So looking at number 7 on page 71, write an iterated integral that could be used to determine the volume of the solid bounded by the surface in the 3 coordinate planes, then confirm your answer with a geometric formula. All right, so first thing we keep in mind is that the surface does appear to be spherical, but if we, based on the picture, also based off the equation itself, but if we square both sides, and get it into standard form, we see that we're looking at a unit sphere. All right, so unit. All right, so if we know the volume of a sphere formula, 4/3 pi times radius cubed, then we can figure out the volume of the whole thing. This appears to be 1 octant, right, because it's bounded by the surface and the 3 coordinate planes, right, based off of the diagram here. That shaded region appears to be the relevant region. That appears to be in the first octant, right? Assuming that, and this is all based off of the way GeoGebra does things, but typically this is the x-axis, with this being the y-axis, and then the z-axis is going up, right, from there. So that's, sort of neither here nor there, because whether it's the x or the y-axis, that's the in the horizontal plane, that's the green or the red. It really doesn't make a difference, because it's still going to be bounded in a single octant, right? Anyway, so if we get 4/3 pi times the radius cubed, radius being 1, 4/3 pi would be the volume of the whole thing. Divide that by 8 and you would have it. All right, what we want to do is use our knowledge of multiple integration to be able to come up with the set of multiple integrals that would do the same thing. All right, so we know that we're going to need to have bounds that define the extent in the x and y direction. So what I'll do here is just get a xy plane. I'm going to take my x squared plus y squared plus z squared equals 1 and let z equal 0. That puts it in the xy plane. In which case we get x squared plus y squared is equal to 1. All right. All right, I could do better than that. / good notes can do better than that. So we're looking at a circle with a radius of 1. And since we're only dealing with, like I said, the first octant, really we just kind of do a top-down view. The only part that would be relevant would be this piece. All right, so that first octant corresponds with the first quadrant of this unit circle. All right, so we would look for bounds that would accomplish finding the volume contained within the surface, but restricted to this region here. All right, so kind of on the path here. We're going to have a double integral z. Now it's a question of dx dy or dy dx. It really doesn't, it's not going to make a difference because of the symmetry inherent in a circle centered at the origin. All right, so x squared plus y squared equals 1. We could solve that for x. That would be equal to plus or minus the square root of 1 minus y squared. We could solve it for y, plus or minus the square root of 1 minus x squared. Either way. All right, so we have a variable relation that restricts the function in terms of either x or in terms of y. All right, so it's just a question of what would be the restrictions beyond that? All right, so if I'm telling you that we can, let's say I want to go with this one. I'm going to choose this one. All right, so that's the variable relationship I want to work with. I'm going to first decide, well, it's only the positive part that I need. I only need the top half. So I'm going to use y equals the square root of 1 minus x squared. All right. So in terms of y, because remember, when we're dealing with y bounds, it's in the form of y equals something on the low end and y equals something on the high end. I think it's pretty easy to see, most people aren't going to struggle with this piece, that on the, well, I wanted that to be 1. Okay, there we go. On the low end, y is going to be allowed to go no further than y equals 0. All right, no further south than y equals 0. All right, so it's how low can you go, how high can you go. All right, it's like that. Oh, I forget what the name of the dealership is. It's the Nissan dealership in Portchester. How low can you go? The guy who does the limbo. And it's weird / funny commercial. Right, so anyway, so we can't go any further south than y equals 0. Now, how far north can you go? All right, well, we can only go as far north as the circle or the semicircle. Oh, that's just wonderful. All right, so let me try that again. I'm going to use an alternative method called the right way. All right, so this is the highest you can go, and this is the lowest. All right, so y equals 0 is our low bound. Our high bound would be y equals the square root of 1 minus x squared. All right, so now that we've decided on that, it's really a matter of saying, okay, we are restricted to these two functions, almost like you don't even need the circle anymore. You know, you sort of disregard that, like pretend it's not there. If I just want this piece here, I got to be thinking about how far left and how far right I can go in order to encapsulate that. All right? Fancy word for a simple idea. So let me use, I'll go back to blue. So I would want to go no further to the left than this location, which is x equals 0, and no further to the right than this location, which would be y equals 0. Not y equals 0. I just felt natural to say that. X equals 1 is what I, in an alternate universe, said correctly the first time. All right. So if we're restricted or bound between 0 and 1, these are our x bounds, then we're in good shape. All right? You could write it like, sort of getting into the habit of doing, / I forget to do it half the time. I almost wrote y again. I mean, I wrote it, but I almost left it there. Y equals 0. I said it, I wrote it, I did a mixture of saying it and writing it. I just can't get out of my own way sometimes. So x equals 0, x equals 1, apologies. So we're looking at dy first, then dx. All right, so our restriction would be, or our x restriction is really a bound for the y restriction. All right, so basically saying I don't need all of my y restricted area. I want to cordon that off. So it's how far north can you go, how far south can you go, and then the x bounds are saying, okay, now that we have that restricted area, now let's restrict the restriction by saying you can't go further west than this location, you can't go further east than this location. All right, so that's a little bit more of a practical way of understanding it, perhaps. All right, so z, we were given z as the square root of 1 minus x squared minus y squared. So it's all this stuff again, just swapping out the z for what it really is. And I could just kind of bring this back so it looks a little nicer. And so that would be your iterated integral. All right. Now, in theory, because again, like I said, this should amount to, the volume of a sphere where I place that p is going to bother me. 4/3 pi times the radius cubed at 1, at a radius of 1, that should be 4/3 pi. So the first octant would just be 4/3 pi divided by 8, which would be really, it's 4/3 times 1 over 8, so the 4/8 becomes 1/2, so it would be 1 over 6 pi. Yeah. So 1 over 6 pi would be the volume, cubic inches. Cubic inches, where am I getting inches from? Who knows? Cubic units. Units. And that's not a 3. It's been a long week. All right, so, and I don't like doing it that way. 4/3 divided by 8. And then just slap on the pi after the fact. All right, so this is what we should end up with after doing all this work. We have our iterated integral, but by the way, this is all they were asking us to do in terms of the main objective of the question. That should give us the 1/6 pi square cubic units. I had it. I slipped. It should give us the 1/6 pi cubic units. So you just want to confirm that by going through the multiple integration technique. So actually anti-differentiating with respect to y, then with respect to x, and you can kind of see here that you're in for like a crazy journey to get there. There's a lot of work involving a trig substitution that you'd have to do. So this part we actually kind of put on hold because this is supposed to be the teaser for the next lesson, which involves, or at the beginning of the next unit, which involves polar, cylindrical, spherical coordinates. All right, so more on that later.